Alright, in this video I'm going to go over how to do interaction diagrams and free body diagrams to show all of the forces acting on a single object. So for this first one, we've got three books stacked on top of one another, and we're going to use these diagrams to show all the forces on the green book. So the first thing we do is the interaction diagram, and here we just look at all of our objects, and I'm just going to call each book blue, red, and green, and we represent each of them by writing them out and just drawing a circle around it green. Okay. Let's also say that the books are on some kind of table or on the floor or whatever. So let's represent that one here. Okay. And now what I'm going to do is I'm going to connect all of the objects that are interacting or that are touching. So the blue book is underneath the green one, the red one is on top of the green book, and then the blue book is on the floor or the table or whatever that happens to be. So each of these lines represents an interaction or a force between the two objects. So the red book exerts a force on the green book, and vice versa, the green book on the red book, and so on. But there's one interaction or one force that's missing from all of this, and it's the one that is interacting with all of them, and that's the gravitational force or gravity. So the object that causes that force is the entire mass of the Earth, so we'll put Earth, and then there is a gravitational interaction between the Earth and everything else. So now we have all of the interactions or all the forces represented. I had said that we wanted to do the forces on the green book. So I'm going to look at the green book here. I'm just going to put a dotted line around that. Physicists would say we are choosing the green book as our system. It's the thing we're going to focus on. And what I do here is I look at all of the intersections with that system boundary. So there's one right there. There's one here from the red book. There's this blue line that goes through here, but it doesn't actually go to the green book, so we don't worry about it. And then there's this intersection here with the line coming from the Earth. So what we've got now are three intersections. So we've got three objects that are causing forces on the green book, and vice versa, the green book is causing three different forces to three different objects. So next up, we need to label each of these forces. Now, all of the forces between the Earth and the objects are gravitational, so we label it F for force, G, little g for gravity. So there's that one. Oop. This one here. And this one right here. These are all the ones coming from the Earth. All of the other forces are surface-to-surface contact. And so when we have just two surfaces in contact with one another, we call that a normal force. It's unfortunately named because this doesn't mean ordinary or regular, but in this case, normal is mathematics speak for perpendicular, and we'll talk about how that comes into play here in a minute. That's a normal force right there. So all of my surface-to-surface contact, these are all normal forces. So we've got two normal forces acting on the green book and one gravitational force. So when I go over here to draw my free body diagram, and the first thing I do is I represent my system as a dot. So I'm representing the green book as a single dot. And now I'm going to draw an arrow showing the direction of each force. So the gravitational force, that always pulls the object down. So we'll draw a vector or an arrow pointing down and label that FG. Now let's look at the normal force from the blue book. So as I said earlier, normal in terms of math and physics means perpendicular. So if we looked at a side view, and let's say that's my blue book, perpendicular to this would be pointing straight up, Remember, perpendicular means there's a 90-degree angle. So when we say F normal of the blue book, we're saying a force that is perpendicular to the blue book. And so we go over here, we go up, and we write Fn for normal, but we also need to include a little more detail to make sure we know which normal force we're talking about, because there's the normal force from the blue book and from the red book. So if we go over to do the normal force from the red book, it's the same idea, except in this case, the red book is on top of the green book. Okay? And so it's pushing down on that green book. And so that's still perpendicular right there. There's my 90-degree angle. So I'm getting a little crowded there. But same idea, label it normal force, but with a little more detail so that I can tell the difference. So there's 3 objects here. So there's 3 objects that are causing forces on the green book. So let's look at another example. In this case, we've got a box sliding down a rough incline. Now, rough here, anytime you see that, that is an indication that there's going to be friction involved. And since it is actively sliding, that's going to be kinetic friction. So if there's active sliding motion, that's kinetic friction. So for the interaction diagram, let's write out all our objects. We've got the box, we've got the ramp, let me call it the incline. So, there we go, the incline. And then we've got the earth, because there's a gravitational interaction between the earth and everything else. So pretty much always going to put the earth on here. So the earth, there's that gravitational interaction, and then the box is on top of the incline. It's touching, so there's going to be a force there. Okay. So since I want to look at the forces on the box, let me draw my system boundary around the box. And so I've got 2 intersections. So I've got 2 different objects causing forces here, but there's a little bit of a trick here. There's actually 3 forces. So first off, let's label the easy one. That's gravity. So that's between the earth and everything else. And we have a surface-to-surface contact between the box and the incline. So there's a normal force here, but that's not the only force between the box and the incline. And this is where friction comes in. There is also a force of friction between the box and the incline. And since they're sliding, it's kinetic friction. So I need to put that K right there. So now we've got 3 forces acting on the box. Normal force between the box and the incline, a kinetic friction force between the box and the incline, and then gravitational force between the earth and the box. So when I go to my free body diagram, I'm going to have 3 vectors or 3 arrows. So I always like to start with FG because it's easiest. Always pulls down. And now here's where it gets a little tricky. If you remember, the normal force is always perpendicular to the surface, which in this case is the incline. So perpendicular to the incline is up this way, because that's where I get that 90 degrees. Okay. If I went straight up, that is not a 90-degree angle, nor is that. Neither of those are 90 degrees, so it's not straight up. It has to point up at this angle. So when I go over here, I have to point up, and then let's make sure to also add that extra detail so that we know exactly what object is causing that normal force. Should call it the incline, not the ramp. Okay. And then lastly, we've got the friction force. Now, friction opposes either motion that's actively happening or motion that's attempting to happen, which in this case we have active sliding motion. And so the box is sliding down and to the right, So friction opposes that up and to the left. So I need to draw that up and to the left. We've got kinetic friction, and then from the incline. I'm running out of room there. So that's it for this one. Let's look at one more. Okay. In this one, we have a child trying to drag a box of toys across the floor, but they're not strong enough. And so the box of toys does not move. And so if we want to look at the forces on the box of toys, let's start with our interaction diagram. I'll just call it box for short instead of box of toys. But when I say box, I mean everything there. So we've got the box of toys, we've got a rope, okay. We've got a child. Okay, there's the floor, and then as always we have the earth as well. Now, one thing people sometimes get confused on, what do we mean, like, why do we have floor and also earth? So when we say the floor or the ground, what we mean is just that area immediately around the object. But when we say the earth, we mean literally every molecule, every atom, every particle that makes up the earth is interacting with these objects through that invisible long-distance force called gravity. So here, the earth, there's this gravitational force between the earth and everything else. The rope is tugging on the box. The child is tugging on the rope. The child's on the floor, and the box is also on the floor. So if I'm looking at the forces on the box, draw my system boundary around the box, and I've got three objects that are causing forces on that box. So always like to start with FG. It's the easiest. Any lines connecting the earth with anything else are gravitational forces. Now if I look at the box and the rope, there's a force there, and that is going to be a tension force. So F with a capital T for tension. And same thing with the child and the rope. That's a tension force. And now all the others are surface-to-surface contact. So the box and the floor has a normal force, as does the child and the floor. Okay. But also, we've got friction happening here. That's what's preventing the box, the child, from being able to slide the box. So not only do we have the normal force from the floor, we also have friction. Okay. And since there is an attempt at sliding motion, but it's not actually sliding, that's static friction. And so remember, static friction is if something is trying to slide an object, but it can't. So I've got four forces. I've got tension, static friction, normal force, and a gravitational force. Okay. So if I go over here, I represent my system as a dot, which is the box. I like starting with gravity because it's easiest. Always points down. The tension in the rope, I have to be careful here. You have to look, if you look here, the rope is pulling up at an angle. So when I draw the tension force, it has to pull up at an angle. Okay. Now my normal force, remember normal means perpendicular, so my force has to be perpendicular to the floor. The floor is horizontal, so perpendicular, oh that's ugly. The perpendicular is straight up. So my floor, or the normal force from the floor, okay, is there. And then the child is trying to drag the box this way, or rather the kid is trying to tugging the box up at an angle. If the box was going to slide, it would slide to the right. Friction opposes that, so friction drags to the left. So our static friction from the floor goes to the left. And so this last example is a pretty complicated one. And so I encourage you to, for all of these, to see how the interaction diagram here relates to the free body diagram, because these are meant to flow from one to the other, and the diagrams should also be consistent. I've got 4 forces over here, attention, static friction, normal force, gravitational force, and I've got those same 4 forces over here.